The next talk this morning will be from Cory Myers from Ohio Wesleyan, and the title of his talk is Parity Measurements in the Strontium-80 Nucleus.
So what is parity? Well, it's hard to explain, but the simple answer is that it's the mirror symmetry of the nucleus, which is analogous to looking at the nucleus in a mirror. If it looks the same, then it's even parity, and if it looks odd, if it looks inverted, it has odd parity. So why are we studying strontium-80? Well, here's a level scheme of strontium-80 created in 1987. The horizontal lines represent the intrinsic discrete energy states. Their values are given above the lines in kiloelectron volts. The vertical arrows represent the gamma ray transitions. Their values are given in the middle of the arrows, also in kiloelectron volts. The numbers off the sides of the horizontal lines are the angular momentum values of the discrete energy states. And the superscripts represent the parity. A plus for positive or even parity, and a minus for negative or odd parity. As you can see, some of these angular momentum and or parity values have parentheses around them. These parentheses represent proposed but not measured values for the angular momentum or the parity. And if you look at sideband 3, you can see that they don't even bother to propose any values for the parity or the angular momentum. So if you look closely, you'll see that there are no proposed or measured negative parity values for any of the discrete energy states. This is highly unusual for a nucleus like strontium-80. Now, if we look at a level scheme of an isotope with just 2 more neutrons, strontium-82, as indicated by these red circles, you can see that there are a plethora of proposed negative and positive parity states. So, why is strontium-80 so different from its neighbor strontium-82 and other nuclei like it? Well, it may not be. This next level scheme was created in 2003 and represents the most recent work done on strontium-80. And as you can see by these red circles here, there are actually proposed negative parity states. And if you look over here at sideband 3, they still don't have proposed parity states for the discrete energy states here. So what we're trying to do is we're trying to conclusively determine once and for all the parities in the strontium-80 nucleus. So we want to get rid of these parentheses here, and we want to actually make measurements for the sideband 3. So how do we remove the parentheses? Well, we measure the experimental gamma ray polarization. An experimental polarization is a measure of how a gamma ray Compton scatters. And for this purpose, we are using a special detector called a clover detector, which consists of 4 individual detectors arranged in a clover leaf configuration. And the schematic is shown here. This schematic is very similar to the clover detectors we're using to make our polarization measure. So essentially what we're doing is we're measuring the number of times a gamma ray scatters horizontally between adjacent detectors, and the number of times a gamma ray scatters vertically between adjacent detectors. And then we're comparing the two. Or if we use the soda can model, Dr. K and 8, we're measuring the number of times a gamma ray scatters from Coke to Diet Pepsi, or from Coke to Sierra Mist. Whether the gamma ray preferentially scatters horizontally or vertically determines whether it is parity changing transition. Then, if we know the parity of the initial discrete energy state or the final discrete energy state, we can determine the parity of the unknown energy state. Here is the experimental polarization formula that we're using to get our polarizations. A is just a normalization factor there to determine if there is a difference in counting efficiency between 2 detectors. In our case, it was found to be 1 using an isotropic gamma ray source with an experimental polarization of 0. Q is the efficiency for measuring the polarization of a gamma ray. And luckily for us, this was already measured for us. N perp is the number of times a gamma ray scatters vertically between adjacent detectors, and N parallel is the number of times a gamma ray scatters horizontally between adjacent detectors. So, how was strontium-80 created? Well, Excuse me. So for a given multiple of gamma ray radiation, such as dipole or quadrupole, we can essentially tell whether the radiation is of electric or magnetic type. This tells us whether the transition is a parity-changing transition or a non-parity-changing transition. So how is strontium-80 created? Well, it's created through an fusion reaction between silicon-28 and iron-54. After fusion, 2 protons were released, and strontium-80 was created in an excited and high-energy state. After production, strontium-80 emitted a shower of gamma rays in order to become more stable. These gamma rays were detected with an array of 10 detectors at Florida State University. 3 of these detectors, shown here in green, are the Clover detectors we're using to make our polarization measurements. Now let's look at some experimental data. Here is an example of data collected showing the number of times 4 gamma rays of particular interest scattered horizontally versus vertically between adjacent detectors. So what we're doing is we're using computer software to subtract the background and fit Gaussian distribution curves to each of these peaks in order to find the areas. We then compare the areas of corresponding peaks between the 2 graphs in order to determine the polarizations. So here's another example of data collected. This shows the 2 polarization measurements that we performed on 2 transitions that are suspected to change the parity of the nucleus between the final and discrete energies, or initial discrete energy states. The experimental polarization is shown here in the second column, and we compared these experimental polarizations with theoretical polarizations, assuming a purely dipole character for the transitions. So our results are dependent on whether or not there's a parity change between the initial and final discrete energy states. So as you can see in our results here, our data is only consistent with a parity changing transition and not a non-parity changing transition. So knowing that these are parity changing transitions, and knowing that the final discrete energy states shown here are positive, we know that the initial discrete energy states are negative parity. So in summary, polarizations were measured for 31 transitions. We verified the ground state band had positive parity. We determined conclusively that the sideband 1 had negative parity. Sideband 2 results were consistent with positive parity. However, we were unable to go either way. They were already measured to be positive, most of them, so. We're totally inconclusive about sideband 3. Couldn't get it. And sideband 5 likely has negative parity. We're inconclusive right now. In the fall, we hope to continue the research to hopefully determine sideband 3 and sideband 5.
Okay, this paper is open for discussion. Please.
So in that first model you showed us, sideband 1, was it measured to be positive parity, or was it assumed to be positive parity?
In sideband, right here?
Yeah, that one there.
Yeah, it was proposed.
It was proposed, okay.
Yeah, premise.
So is it just a change in the model?
Yeah,
or
we
we actually
actually-
have true measurements?
Yeah, we actually determined that was negative.
Okay.
Just so I understand, when you talk about vertical versus horizontal scattering, vertical just by definition means it goes from one detector to the one above it. It doesn't mean literally, in other words, a whole range of angles that could qualify as a vertical scatter. Is that what
It's
that
like-
means, or?
It's like perpendicular to the reaction plane. That's so, yeah, it's just up from the initial detector that it was incident on.
Are the widths of the arrows transition probabilities? Is that what that's indicating? Or why are some of the arrows really fat and some of them are really narrow?
I forget why that is.
Yes. But also, just to elaborate a little bit on your other question, what matters is the direction of the electric field vector as these gamma ray, in the electromagnetic radiation that is the gamma ray, that are the gamma rays. So basically what he's doing is you can essentially tell the difference between whether the electric field vector is jiggling this way or this way, difference between electric or magnetic radiation, based on how these gamma rays come and scatter in these special detectors. And what matters is how that field direction is oriented relative to the reaction plane in which these nuclei are made.
Does everything flip theoretically if you have quadrupole versus dipole? In other words, you have to know clearly that I'm dealing with dipole radiation coming out, or you have to know that I'm dealing with quadrupole to make your parity assumption?
From what I've done, it's been mostly like there's a mixing ratio, and we've performed like the polarization graph shown in the last one. From what I've done so far, we've only determined for like a not or a zero mixing ratio, or it's clearly one or the other. So Dr. K would know one.
Well, just quickly, someone else has done the work for us to determine whether many of these transitions are to dipole or quadrupole. It's up to us to figure out whether they'll be magnetic or electric type. Okay, why don't we thank our speaker again.